Hello everyone, welcome back to my channel. I know it's been a minute, but I'm finally back. And on today's video, I'll be going through the IGCSE Physics paper 42 for the May-June 2025 series. And if you're new here on this channel, I'll be doing IGCSE Physics content. So anything from past papers, topic questions, and overall revision. So if you're interested, make sure to subscribe so you won't miss out on any content. But let's jump in today's video. Right, first question. Figure 1.1 is a speed time graph for an ice skater. Okay. Describe the motion of the skater between time 0 and time 3 seconds. Okay, so 3 seconds is about here. So basically, it's a straight line. So on a speed time graph, a straight line means that it's in uniform motion. So we can say it's in constant motion, or we can say constant speed. Constant speed. That's going to be our answer. Let's move on to B. Calculate the distance traveled by the skater between time 0 and time equals 3 seconds. Okay. So distance. Distance is always the area under the graph. So between time 0 and time 3, the same thing. So if we do this is time 3, it's going to be a rectangle. So area is going to be base times height. Not base times height, length times width. So length is from 0 up to here. If we zoom in, we know this is 11. And this width is going to be 3, from 0 to 3. So 11 times 3, which equals 33. It's going to be 33 meters. That is the distance traveled. Part C, state what is meant by deceleration. So deceleration, it's the rate of decrease in velocity. It's basically the opposite of acceleration. Acceleration is the rate of change of velocity, but then it's in the positive one. It's when it's increasing. So deceleration, it's the rate of change of velocity, but then it's in the negative. So basically you can say it's negative acceleration. That's also a valid answer. Part 3, draw a tangent to the graph at 9 seconds, okay? Use a tangent to calculate the deceleration of the skater at time equals 9 seconds. So we know that deceleration is basically negative acceleration. So acceleration from a speed time graph, it's going to be the slope or the gradient of the graph. So at time 9 seconds, it's over here. Now we have to draw a tangent to the graph. So a tangent is basically a straight line that touches only this point on the graph, only this point. So let me try doing that. Don't really have a ruler, so it's going to be a bit hard. Nope, let me try it again. Let me try it again. So after a few tries, I think I drew a tangent. So this is a line. I know it's not a straight line. It's difficult to do it without a ruler. But basically what you want to do is you draw a straight line only touching this point, no other point on the graph. So after doing that, we pick 2 points, any 2 points. So for me, this seems easier. This point, which is basically 6,4. And also I can pick this point, which is, so this is 10 This is 11. So it's going to be 10.246, 10.6. So this point is going to be 10.6, comma. If we go along the y-axis, we know this is 1. It's going to be 0.24, 0.4. So 10.6, 0.4. Those are our points. After that, we just have to find the gradient using these 2 points. So gradient or deceleration is equals to y2 minus y1 over x2 minus x1. So from our coordinates, y2 is 4 minus 0.4 over 6 minus 10.6. 6 minus 10.6. So if we do that, let me just calculate that. So you're gonna notice the answer is gonna be negative, 0.78. The answer is gonna be negative, but since we're asked for deceleration, we just ignore the negative and write the answer 0.78 meters per second squared. Now it might not be entirely accurate since I didn't use a ruler to perfectly draw the line, but if you use the ruler, you're gonna get an answer which is within the range given on the mark scheme. But this is the gist of it. Question number 2. Figure 2.1 shows a balanced uniform meter rule made of wood. Okay, the width of the meter rule is 2.6 times 10 to the power of minus 2 meters, and the thickness of the ruler is 6 times 10 to the power of minus 3 meters. Okay, define moment of a force in words. So moment is force times the perpendicular distance. The perpendicular part is very important. It's the force times perpendicular distance. Part B. On figure 2.1, mark the position of the center of gravity. Oops. Center of gravity of the meter rule was a point labeled x, labeled the distance x from 0 centimeter end of the ruler. Okay, let's see. So this is a uniform meter rule. So that means the mass is distributed equally across the ruler. So which means since it's a 100 centimeter ruler, the center of gravity is going to be around 15 centimeters, halfway line. So if this is 42, that means 50 is going to be somewhere around here. So we label this x, and this is 50 centimeters. This point. C. Show that the mass of the meter rule is 0.081 kilograms. Okay, so now this is a moments question, and it's 3 marks. So let's see what we can do. So the pivot is at 42 centimeters. Let's not forget that. So first, we use the conservation of moments. So the anti-clockwise is equals to the clockwise moment. So since we know that, let's calculate all the anti-clockwise moments. So this one is anti-clockwise, 0.34 newtons. Okay, so 0.34, and the distance from the pivot is going to be, it's at 10 centimeters, pivot is at 42, So 42 minus 10, that's 32. Times, since it's centimeters, we should use meters, but then we're using centimeters throughout, so it's going to be okay. Times 32. This is supposed to be equals to the whole of the clockwise moment. So this one, we have two. The first one is obviously this one, the 0.12 Newton, times the 80 centimeters. So 40, we have to have 80 minus 42, which is 38. The distance between the pivot and this mark over here. But also, we have the center of mass of the ruler, which is at the 50 centimeters. So the center of mass is where the mass acts, the mass of the object acts upon. So basically, it's going to be, so now we don't know the mass of the ruler. So we have to prove it. So let's say the mass of the ruler is m, and we have to use the weight. So we do m times 9.8. And then this is multiplied by the distance. So 50 minus 42, that's 8 times 8. So now we just have to find m. So 0.34 times 32, that's 10.88. And 0.12 times 38, that's 4.56. Plus, so 9.8 times 8, that's 78.4 m. So now we just have to solve for m. So it's going to be 10.88 minus 4.56. This divided by 78.4. We get m equals 0.0806. So two significant figures, that would give us 0.081 kilograms for the mass of the ruler. So we have proved it. Hopefully I didn't make it a bit more complicated than it has to be. So basically, it's in equilibrium. So the clockwise moments, the anti-clockwise moments should be equals to the clockwise moments. So here we have only one force, the 0.434 Newton force. So we find this moment, but here we have two forces, the weight of the ruler and the weight of this block over here. So we add these two, it should be equals to the moment of this one. That's how we found m. Part 2. Calculate the density of the wood of the meter ruler. Okay, what do we know? We know that density is mass over volume, and the mass is 0.081. Now the volume. We don't have the volume, so we have to find the volume. So volume is length times width times height. So length is 100 centimeters, which is 1 meter. So times width. If we go back to the diagram, we know width is 2.6 times 10 to the power of minus 2. Minus 2 times height. Also on the diagram, 6 times 10 to the power of minus 3. So if we put this in the calculator, we get density is equals to 519 kilograms per meter cubed. But since if we want to do 2SF, we can write it as 520 kilogram per meter cubed. That's going to be our density. Next question. Define momentum. So momentum is defined as mass times velocity. Part B. Figure 3.1 shows two toy trains A and B on a track. Okay. The mass of train A is 0.45 and the mass of train B is 0.21. The trains do not have motors. Okay, train A travels towards train B and they collide. Immediately before the collision, velocity of train A is 0.34 to the right. So if you draw this, 0.34 meters per second. And velocity of train B is 0.12 meters per second. The trains stick together when they collide. Calculate the velocity of the trains immediately after collision. So they told us a very important fact here. The trains stick together when they collide. Okay, so we use conservation of momentum. The momentum before collision is equals to momentum after collision. So basically, the momentum, let's calculate the momentum before collision. So if you look at train A, we have mass 0.45 times it's moving at 0.34 meters per second. Plus, we got momentum of B. So mass of B is 0.21 times the velocity. Now this is the tricky part where people lose mark. Velocity is 0.12, of course, but it's in the opposite direction. So we use minus 0.12. And then when they combine, they start moving together, or when the trains stick together, we add their masses. So it's going to be 0.45 plus 0.21. And then the velocity. The velocity. Their velocity immediately after collision, we call that v. Now we just have to solve. So 0.45 times 0.34 plus 0.21 times times minus 0.12. That gives us 0.1278. This is equals to 0.45 plus 0.21, 0.66 v. So divide both sides by 0.66. V equals 0.1278, 0.66. We get 0.19 meters per second. So velocity is 0.19 meters per second. So now we found the velocity. How would we know the direction? So notice how it's not negative, it's positive. So that means since when we're doing our calculations, we decided positive was to the right, that means since we get a positive, direction is right, not left. If it was negative, it would have been left. Part C. A different train is traveling with a momentum of 0.26. Okay, the train slows down and stops after 2.1 seconds. Calculate the average force acting on the train during this time. Okay, so we have a train here. Sorry about my bad drawing. Let me just add the wheels. It's moving at a momentum of 0.26. This is momentum, not speed, not mass. And then it slows down and stops after 2.1 seconds. So now we have to find the force. So we know force is change in momentum over time. So what's going to be the change in momentum? So change in momentum is initial momentum, we can call that, or final momentum minus initial momentum over time. So final momentum, we know that it has stopped. So that means velocity is 0, that means momentum is 0. So it's going to be 0 minus initial momentum is 0.26. And we got a time of 2.1 seconds. So it's going to be minus 0.26 over 2.1. Minus 0.26 over 2.1. And then we get minus 0.12 newtons of force. And now we have to include the minus because the direction of the force is in the opposite direction. That's why it's slowing down. That's why it stops. Part 4a. Figure 4.1 shows two metal containers, A and B. Container A has a dull black outer surface, and container B has a shiny white outer surface. A and B both contain very hot water at time 0. The temperature of the water in each container is recorded every minute. Part 1. State which container has the larger temperature change over the first 5 minutes. Explain your answer. Okay. Which container has a larger temperature change? So we know that the temperature is going to be dropping. So the one that loses its heat faster, it's going to be container A. The dull black outer surface. So why is that? Because dull black surfaces are better emitters of radiation. So since they are better emitters of radiation, they will lose their heat faster. So the temperature decreases faster. After 30 minutes, the temperature of the water is in the container A remains constant. Okay, so that means there's no transfer of energy. There's no net transfer of energy. State in terms of energy transfers why the temperature remains constant. Okay, so whenever the temperature remains constant, that means the rate of transfer of energy out of the container is the same as rate of transfer of energy into the container. So we can say rate of transfer of energy out of the container is the same as into the container. So basically they cancel out each other, so there's no change. Experiment is repeated without lids on the containers. Say the name of additional method of energy transfer that occurs. So if the containers have no lid, there's hot water. So when the air near the water is going to be warmed up, so it's going to rise up, and then the cooler air comes down, causing convection current. Basically, it's convection. This is how liquids and some gases lose heat or transfer heat energy. Convection. Figure 4.2 shows a metal pan with a wooden handle. Okay, so this is the wooden handle. The rest of it is metal. Explain why there is a much greater rate of transfer energy through the metal than the wood. All right. So we know that metal is a good conductor of heat. But why? We have to explain why. So basically, metals contain free delocalized electrons. And these electrons, they carry thermal energy throughout the container. So when they're carrying these thermal energy and they collide with the other particles, that way the thermal energy is transferred. So let me draw a structure of a metal. If you're doing chemistry, you'd understand it even more. So we have electrons in metals. If these are the metal particles, we have electrons. So whenever heat is transferred, these electrons, they're free to move anywhere. So they would carry the thermal energy, they would move, collide with this particle. And this particle would collide with the other one. This electron is also free to move. So these electrons, they carry thermal energy and they can move anywhere. So they transfer that thermal energy. But wood does not have those delocalized electrons. That's why it cannot, it's not a good conductor. Question 5a. Describe an experiment to determine the speed of sound in air. State the apparatus required, the measurements taken, and how to calculate the speed of sound in air from the measurements. You may draw a labeled diagram as part of your answer. 4 marks. Okay. So we can use different methods. So let's try using the an echo method. So to use the echo method, we need a stopwatch and someone to like clap to produce a sound. You can use any way to produce a sound. So let me draw the diagram first. So we can have someone clapping. Again, forgive my bad drawing. We have someone clapping. And then we have like a wall around here. And then we use a timer or a stopwatch. So what we can do is when one person claps, when that clap is heard, you start the timer, and then after you hear the echo, you stop the timer. Now we have the time, and then we can use a measuring tape to measure this distance. This distance, let's call it d. So now we have the time, and we also have the time and also the distance. So now we can calculate the speed of sound. So how can we write this? We can say clap at a distance d from a wall, and then use tape measure to measure d. So after that, and then after that, start stopwatch when clapping, and stop after hearing the echo. And then after that, we use the speed formula. And then speed is equals distance, or we can say d over the time. But since when echo is heard, the sound travels this distance, and then it also comes back. So it travels it twice. So it's going to be 2d divided by time. That's the speed of time. I mean the speed of sound in the air. Bluetooth is used to connect a mobile cell phone to headphones. State the name of region of electromagnetic spectrum used by Bluetooth. So Bluetooth uses radio waves. Mostly Bluetooth, Wi-Fi, they use radio waves. State the speed of electromagnetic waves in air. This speed is the same as speed of sound, speed of light in air, which is 3 times 10 to the power of 8 meters per second. Part 3. The frequency of a Bluetooth network is 2.48 gigahertz. Calculate the wavelength of the waves used in the Bluetooth network. So we can use the speed formula, V equals lambda f. So we know speed is 3 times 10 to the power of 8. We don't know wavelength times frequency. So they've given us a frequency which is 2.48 gigahertz, but we have to convert this into hertz. So giga means times 10 to the power of 9. So it's going to be 2.48 times 10 to the power of 9. So divide both sides by 2.48 10 to the power of 9. 2.48 times 10 to the power of 9. So in this case, we get lambda equals lambda equals 0.12 meters, of course. That's our wavelength. So make sure to convert the gigahertz into hertz. Question 6a. Figure 6.1 is a full-size diagram of a lens and an image eye of an object. Focal length of the lens is 3 centimeters. Okay. On figure 6.1, mark 2 points with labels F to show the position of the principal focuses or the focal points of the lens. So focal point of the lens, they already told us the focal length is 3, which means it's 3 centimeters apart. So somewhere around here. Now this is drawn to scale, so make sure you use your ruler. So this is F, and also somewhere around here, F. Make sure this distance from the center of the lens is 3 centimeters, and also this distance to the point is 3 centimeters. On figure 6.1, draw 2 rays from image I to locate the object and label it O. Okay, so they told us this is an image. Now we have to draw 2 rays to locate the object. So if we can draw 2 rays, one of them is going to go through the center of the lens. So it has to go through here. It goes through the center of the lens, and the other one, it has to go through, it has to go straight, or it can go through the focal length, this focal length, and then goes straight. Make sure this lens goes through the point. So basically, our image is going to be over here, or our object, and then we label this O. The object is moved so that it's 6 centimeters to the left of the lens. So it's 6 centimeters to the left of the lens, somewhere around here. So state 1 characteristics of the image formed when the object is in this position. So let's try drawing lines. Let me just use red lines. If the object is here, object is here. Let's say this is 6 centimeters. So when we draw the ray lines, we have a red one here. We have this one here. Intersect at this point. So the image is going to be, one of the characteristics is going to be, it's going to be inverted. or it's also enlarged because it's bigger. Yeah, but then only one characteristic is needed. Next question. Figure 6.2 showed a simplified diagram of an eye with rays from a near object. The eye needs connection for long-sightedness. Okay. On figure 6.2, draw a path of rays inside the eye to show the effect of long-sightedness. So long-sightedness happens when we got the lens, and then if you continue this diagram until here, it's going to be the same, but then now they're going to start converging. But the problem is when they're converging, they're going to converge behind the retina. That's why it's blurry. So when they're converging behind the retina. Make sure you use a ruler, but make sure that the converging point is behind the retina. That's why it's converging. I mean, it's long-sightedness. In a short-sightedness, it's going to be the opposite. They're going to converge maybe around here, in front of the retina. A lens is used to correct long-sightedness. Draw the lens suitable for the correction. So it's going to be a converging lens. It's going to be you can draw any converging lens. So what happens is when you put a converging lens maybe here, they converge earlier on. So the conversion happens earlier on. So the image forms not behind the retina, but on the retina. Question 7. State what is meant by an electric field. Electric field is it's a region. First of all, it's a region where a charge experiences a force. It's basically like a magnetic field. Magnetic field is a region where a magnet experiences magnetic force. So electric field is the same thing, but with a charge instead of a magnet. A plastic rod is rubbed with a cloth. The plastic rod becomes negatively charged, and the cloth becomes positively charged. Why is that? So, because of friction, electrons move. Now, it's the electrons that move, not the protons. So, electrons move from the cloth because since electrons move from the cloth, into the rod, that means the cloth has less electrons, so that means it has more positive particles, so it's positively charged. So move from the cloth to the rod. So in diagram, maybe we have the cloth over here, then we have the rod. So what happens is there's equal number of charges in both. So when they're rubbing each other, the electron moves here. So now there is only one negative maybe, and then there's two more negative charge. So this is negatively charged. This becomes positively charged because there are more positive particles. The negatively charged plastic rod is suspended by an insulating thread. Okay, another negatively charged plastic rod is brought close to the suspended rod. State what happens to the suspended plastic rod. Okay, we should try to understand this. So we have a negatively charged plastic rod, basically this one, and then it's suspended by an insulating thread. Okay, so it's hanging. It's negatively charged, and there's an insulating thread. Another negatively charged plastic is also brought close to the suspended rod. So we got another one. Oh, yeah. So what happens when they're close to each other? It moves away. When this is brought close to each other, this one moves away. Why? Because it's repelled, because they're the same charge, due to the same charge. So like charges repel each other and opposite charges attract each other. Part C, define the kilowatt hour in words. So kilowatt hour, it's in the name. So it's the energy transferred in 1 hour. In 1 hour at a rate of 1 kilowatt. So basically, it's the energy transferred in 1 hour at a rate of 1 kilowatt. So that's what kilowatt hour means. It's the energy transferred when 1 kilowatt is transferred in 1 hour, basically. A small lamp illuminates an electric oven. The lamp has an output power of 25 and operates for 220 hours in a year. The PD across the lamp is 230 volts. Calculate the energy transferred by the lamp in 1 year. Give your answers in kilowatt hours. Okay. So first of all, so we know that power equals IV and energy equals IV. So if power equals IV, then power is, we have 25 watts. So we don't need this formula. We know energy equals IVT. So IV, that's a power, it's 25 watts. And time is 220. But the problem is this 25 watts, it's in watts, and we have to have it in kilowatts hour. So we divide by 1000. So 25 over 1000 times 220. So it's 25 times. So we get 5.5. And the unit is going to be kilowatt hour. That's how we do it. Calculate the current in the lamp. Okay. So from the previous one, we know power equals IV. We have the power, which is 25 watts. I, we don't know, and then 230 volts. So divide both sides by 230. And then 25 over 230, that gives us 0.11 amps. Don't forget the units. Question number 8. It's about magnets. Figure 8.1 shows a simplified diagram of an AC generator. State the names of the components P and Q. So this P and Q, this rings, it's an AC generator. So they're going to be called slip rings. If it were a DC generator, it would have been split rings. X and Y. X and Y are brushes. Explain why an EMF is only induced when the coil is turning. So we have magnetic field, this direction, let me just draw it in red. Magnetic field in this direction, from north to south. So when the coil is turning, it's cutting the magnetic field. That is the only way an EMF is being produced. So the coil cuts the magnetic field when it's turning. State one possible change that causes a larger EMF to be induced. So one of them, it can be, we can increase magnetic field strength. Let me try that again. Increase magnetic field. We can also increase the speed of rotation of the coil. So if we rotate it faster, more EMF is going to be induced because the magnetic field is going to be cut more times. We can also increase the number of coils. All three are valid answers. Figure 8.2 shows a circuit diagram. Resistors A, B, C, D are identical. The resistor A is 2.4 amps. Since they're all identical, they're all 2.4. Oh, it's the current in the resistor. Never mind. So I is 2.4. I is the, sorry about that. I is a total current, and the current here, that call it IA, it's 2.4. State the value of the current in resistor B. Explain your answer. So if we look at the diagram, they're all connected in parallel. So voltage is the same. Here, 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 here. It's always the same. So basically, it's the current that's changing. So if we have 2.4 here, and then we have two resistors here, which are identical to A. So that means we have 2 times the resistance here. So we know V equals IR, and if we made I the subject, I equals V over R. So if R increases, I decreases. So if R increases by 2, that means if R doubled, which it did because of B and C, that means I halves. So it's going to be 2.4 divided by 2, which is 1.2 amps. Because the resistance doubled. And I is inversely proportional to R. Calculate the value of current I. Okay, so now we use the same thing. Here it's 2.4, here it's 1.2. Here it's the same thing. It's going to be 2.4 because there's only one resistor. So we add 2.4 plus 2.4 plus 1.2. That gives us 6. So it's going to be 6 amps. So 2.4 times 2 plus 1.2. That's how we got 6 amps. Part 3. The reading on the voltmeter is 5. Calculate the resistance of A. Okay. Voltmeter is 5. Okay. So volts is 5. Current is 2.4. Now we have to use V equals IR. So using that, R equals V over I. So V is 5, I is 2.4, 5 over 2.4. That's going to give us 2.1 ohms. That's going to be the answer. Question number 9. State what is meant by background radiation. So background radiation is radiation that's always present in the environment. Radiation always present in the environment. So there are different sources for this radiation. It can be from radon gas, it can be from rocks, it can be many reasons. So, question part 2. State one source that makes a significant contribution to background radiation. Oh, one of them is radon gas. Another one, rocks. There are multiple ones. We can write cosmic rays. Part B. Radioactive isotopes are used in some medical treatments. Radium-223 is an isotope of radium. Radium-223 decays in emission of alpha particles to an isotope of radon. Okay. Oh, I mean radium. So radium becomes radon. Complete the nuclide equation for the decay. So first of all, we know alpha particle has mass number of 4 and 2. So now we just have to solve the equation. So 223 minus 4, that gives us 219. 88 minus 2, 86. So these two, when they're added, should give 88, and these two, when they're added, should give 223. Radium is injected into the body to treat specific organ. Explain why the source must be inside the body. Okay. So basically what it's saying is radium is used to treat specific organs. So we need when radium decays, we need the alpha particles to reach those specific internal organs. But the problem is alpha particles, they don't have good penetration, unlike the gamma particles. So that means they're not gonna be penetrating the skin. So we can say alpha particles can be stopped by the skin. They cannot penetrate the skin by the skin. Part C, an isotope of technetium is injected into the body to detect cancer in one of the organs. Okay. The half-life of this isotope is 6 hours and it decays by emitting gamma radiation. Radiation is detected outside the body. Explain why a source of gamma radiation is used. This is so that the gamma particles can be detected outside the body. The body. And part 2, explain why a source with a short half-life must be used. So always when the radioactive isotopes are used in the body to treat, a short half-life must be used because a long half-life might mutate the tissues or might damage the tissues. So we can say long half-life will cause damage to tissues. Number 10. I believe this is the last question. Yep, it's the last question. All right. Table 10.1 shows data for planets A, B, C, D. All right. Part 1. State and explain which one of these planets is closest to the sun. So we got, all right, let's see. So first we can look at surface temperature. This one has the highest one, so it's this one. It's planet B because it has highest temperature because it's the closest to the sun. Okay, part 2. Calculate the surface temperature of D in degrees Celsius. Okay, D is 53 Kelvin. So to convert to degrees Celsius, what do we do? It's minus 273. So 53 minus 273, that's minus 180. It's actually very cold. So basically, 1 Kelvin is 273 degrees Celsius. That's what we need to know. No, I got it the other way. 1 degree Celsius is 273 Kelvin. An object falls through a height of 2 meters on Earth on each of the planets in table 10.1. State and explain on which planet the object falls 2 meters in the shortest time. Ignore any effects due to the atmosphere. So basically, if we want the shortest time, that means we need the maximum amount of gravitational field strength. So which one is it? It's planet A with 23. So we can say planet A. It has the highest gravitational field strength. So that means there's going to be more acceleration basically. So the acceleration of objects is going to be 23 if there's no air resistance in this planet A. Okay, figure 10.1 shows the stages in the life cycle of a massive star. Key point, massive star. Okay, I complete figure 10.1 by adding the correct terms. Okay, massive star expands. Then after that, it's going to be red supergiant. So after that, it becomes a supernova and nebula. So nebula is like this cloud of gas, and this cloud of gas contains hydrogen. And then leaves behind. So this, it can be multiple things. So if it's a massive star, it could leave a black hole. That's one of them. Or it can leave new stars, new smaller stars. So make sure you understand the life cycle of a massive star and also a smaller star. Last question. State the quantity that the brightness of supernova in a galaxy can be used to determine. So the brightness of a supernova can determine the distance to a galaxy. And then the other thing is redshift. It can be used to determine time. So if redshift determines the time and the brightness of supernova determines the distance, there's actually a formula for it to determine the distance, which you don't need to know currently. So if we have these two, and then we can find Hubble's constant. So that's it for today. I hope you guys enjoyed. And then if you have any questions, comments, make sure to drop them down below. And until next time, see you.